Start recording. I hope that you guys are having a good day. We have an exam on Monday. Our exam is just going to be like the other ones, where it's going to open at 12 and it's going to close at 6 p.m. You got to be done by 6 p.m. because that's when it's going to close. I will be posting some top hat stuff from Tuesday, Thursday, and today. And what I'm going to have is I'm going to post quite a few more top hat items, and they are all going to be due 1 week from today, which 1 week from today will be our final exam. So all the top hat, nothing will be due on Monday. Everything will be due on 1 week from today, which is the 28th of June. I'm going to provide y'all with some more details about the final exam after Monday, so after exam number 4. And with that, the only other thing that I wanted to say about this upcoming exam was that this upcoming exam won't have as much content because we've only had 3 days worth of content as opposed to 4. But one of the challenges with this material is that enzyme inhibition and understanding the different plots, the graphs, that's a tough thing to kind of wrap your mind around. That's always kind of challenging. So definitely give yourself the time to understand those. I think in my video, I make recommendations of like, just draw the plot and say, okay, if my no inhibitor and plus inhibitor intersects on the x-axis, what type of inhibition is that? What if it's an intersection on the y-axis? Then what does an inhibitor bind? If my inhibitor is able to bind only to the free enzyme, what type of inhibitor is? If my inhibitor can bind to the enzyme substrate complex, what type of inhibitor? And then what type of inhibitor is it if my inhibitor, which that's one of those words you say it so often it kind of sounds silly, if my inhibitor can bind equally to the free enzyme and the enzyme substrate complex. So kind of navigate and try to think about those different things. And then what's changing? Is my Vmax changing or is my Km changing based on the presence of an inhibitor? So what I wanted to talk about today is lipids. This will be on your exam today. Yes, you will have a quiz today. That quiz will be open at 4 p.m. And it will close tomorrow at 2 p.m. And I would anticipate questions about the graphs, the Lineweaver-Burke plot, and what the inhibitors bind, just as a little bit of a hint there. But we've got a quiz today. It will close tomorrow at 2 p.m. It opens today at 4 p.m. Then, let's see. Yeah, today is going to be lipids. We're going to discuss lipids. And this will be on your exam on Monday. And this will really set the table for our discussions next week on membranes. Okay. And then after lecture, if anyone has any questions, I'm more than happy to spend a little bit of time answering those questions for you. Okay, so here we go. Lipids. These are substances of biological origin that are soluble in organic solvents. This is an important thing to remember because most of what we talk about in an aqueous environment as opposed to in an organic solvent or an organic environment. Now, lipids perform 3 major biological functions. They form a bilayer. Bilayers are essential components of biological membranes. They contain hydrocarbon side chains, and they serve as energy stores, and they are heavily involved in signaling. So our big items there are, they are components of membranes, they are energy stores, and they are involved in signaling. Now, in terms of the classes of lipids that we're going to talk about, fatty acids, triacylglycerols, glycerophospholipids, sphingolipids, and steroids. I think that most people are familiar with lipids in the context of triacylglycerols or fatty acids, in part because if you go get your annual physical and they do blood work on you, they're going to do what's called a lipid panel, and that lipid panel will look at your triacylglycerols and your free fatty acids. So those are the ones that we think about, or I typically think about as dietary lipids. But we're going to get into all of them. So fatty acids. Here are a total of 4 different fatty acids. One of the things that I want you to recognize about them is the groups that I'm circling here. Oh, I don't know why that happened. These are all carboxylic acids. Then each one of them has a carbon labeled 1. If we go to the very bottom of this structure, we have a carbon labeled 18. Okay, so these are 4 different 18 carbon long structures. Now, if you look below that carbon 18, you'll see that they have unique names: steric, oleic, linoleic, and alpha linolenic acid. Okay, so these are 18 carbon long molecules with 4 different names. Well, something has to be different about them. Now, with that, or before I go into that, what I do want to caution you about, and maybe not caution, but kind of prepare you for, is I am not going to expect you to know common names of fatty acids. As you continue your studies in biochemistry and in life sciences, there are going to be some fatty acids that are a little bit more common for you to encounter, especially if you go into like a healthcare related field. You might talk about some fatty acids more than others, but these names at the bottom, these common names, I have no expectation that you memorize these or anything like that. Okay, so steric acid, oleic acid, they're both 18 carbons. The difference between them is this right here. There's a single double bond present in oleic acid that is not present in steric acid. Then we go on to linoleic acid. We have two double bonds. Alpha linolenic acid, we've got 1, 2, 3 double bonds there. So we have a single, double, and a triple, or 1, 2, and 3 double bonds that differentiate oleic, linoleic, and alpha linolenic acid. Now, these fatty acids, one thing that they are is they are all carboxylic acids with long chain hydrocarbon side groups. The predominant fatty acid residues in plants and animals are 18 or 16 carbons long. Now, this terminology here, saturated and unsaturated, this is terminology that you definitely get into in organic, but it's a big part of our discussion of fatty acids. It's also a big part of a discussion of nutritional lipids and dietary lipids. For instance, if you go to a physician, if you go to a dietitian, and ask them, "Hey, I'm going to eat a diet that's basically going to have every single different type of nutrient. I'm going to have carbohydrates. I'm going to have protein. I'm going to have fats. Is there one type of those molecules that I should either not completely avoid, but have a smaller amount of?" And they're going to say, yes, you should have less saturated fatty acids. Now, we'll get into the reasoning behind that in just a moment, but our saturated fatty acids, one saturated fatty acid is steric acid. So when you think about a saturated fatty acid, I want you to think about a fatty acid that has no double bonds. Now, this is the thing that I always bring up, and then someone says, "Oh, but what about the carboxylic acid?" And I say, "You're right. There is a double bond in the carboxylic acid, but that is not one of the fatty acid, or that is not one of the double bonds that we're thinking about when we're distinguishing between a saturated and an unsaturated fatty acid." If you look at oleic, linoleic, and alpha linolenic acid, these are all unsaturated fatty acids. They have at least one double bond. Now, this nomenclature notation to identify them. So you have to know the difference between a saturated fatty acid and unsaturated fatty acid. This notation right here, the C18:0, that right there corresponds to, well, the number of carbons, 18. We're talking about a fatty acid with 18 carbons, and then this :0 indicates that this fatty acid has no double bonds. Compare that to 18:2. Now, would anyone like to add to the chat from this slide, which fatty acid is an 18:2 between steric, oleic, linoleic, and alpha linolenic acid. Which one of those has a pattern of 18:2? Perfect. It's linoleic acid. Linoleic acid is a polyunsaturated fatty acid that has two double bonds. So 18:2. Now, if we were to look at alpha linolenic acid and classify it or name it using that same scheme, we would say C18:3. Is everyone good with that? Okay. Now, when it comes to fatty acids or our double bonds are all going to have this cis configuration, because one thing that is important to know dietarily is that fatty acids that have the trans configuration are generally unhealthy. They're not digested in the same way as cis fatty acids. So lots of what we'll discuss are naturally occurring fatty acids or forms of fatty acids that are naturally occurring. Now, typically the first double bond is found between carbons number 9 and 10. In polyunsaturated fatty acids, the double bonds are not conjugated. Okay, so that terminology, whenever I hear that, not conjugated, what does that mean? Well, if we look at linoleic and alpha linolenic acid as an example, I always like to translate that double bonds are not conjugated to something that really is like, I don't know if I guess it would be like, I'm going to translate that or convert that to something that makes sense to me. Now, I'm going to clear all my markings on this slide so that I can say, okay, let's take into consideration all of this information, specifically these last two bullets. The first double bond is generally between carbons number 9 and 10. Okay, so we've started from the top where we have carbon number 1, and then we count all the way up to carbon number 9. We've got a double bond between carbons number 9 and 10. Got it. Next, I'm looking at linoleic acid here. In a polyunsaturated fatty acid, which linoleic acid is a polyunsaturated fatty acid, the double bonds are not conjugated. Okay, so linoleic acid is my model. I have double bonds that are not conjugated. Okay, so linoleic acid has double bonds that are not conjugated. So what does that mean? That means I've got a double bond followed by a single bond, followed by another single bond, followed by a double bond. So if I'm drawing a fatty acid and it has 3 double bonds, for instance, I'm going to draw it as double bond and then 2 consecutive singles, then a double, 2 more consecutive singles, and then a double bond. So whatever it says, or whenever you see this, that double bonds are not conjugated, it's going to be double, single, single, double, single, single, double, single, single, double, until, well, you're done. Because if these double bonds were conjugated, it would be double, single, double, single, double, single, double, single. Okay, so that's kind of your naturally occurring pattern and organization for your double bonds in a fatty acid. Okay, does anyone have any questions about this? Now, I'd love for any questions, but if you don't have any, I'll ask that, and then I'm going to move on. I'll give it like a 3 count, and then I'll move on. This is being recorded just like all of our other lectures, so you can scrub back, but also don't hesitate to stop me, and I'll bounce back a previous slide. So this is a good look at saturated fatty acids as well as unsaturated and polyunsaturated fatty acids. Now, one thing that's important that we look at right here before we proceed is that when we were placing these double bonds, we started with our carboxylic acid carbon as being our highest priority carbon that got carbon number 1, and then this methyl group at the end got carbon number 18 as the numbering based on, our rules from organic. Now that is always going to be true, but there's this other numbering scheme. Now this is something that you've probably heard of. For instance, lots of nutritional advice that surrounds fatty acids is reduce your amount of saturated fatty acids and increase the number or volume of omega fatty acids that you eat, specifically omega-3 fatty acids. If you go buy milk or eggs, you'll see something like, eggs with additional omega-3 fatty acids. Now, what this omega numbering scheme is a little bit confusing, in part because this omega -3 right here. So this is your lowercase omega symbol. The omega symbol you might be a little bit more familiar with looks like this. But this is kind of your lowercase omega. Now, if you think about beginning and end, the alpha is the beginning, omega is the end. So our methyl end of our fatty acid is our omega carbon, our terminal carbon, our last carbon. Omega -3. If we are going to look at a molecule and draw an omega -3 fatty acid, we are going to start from our methyl end. And we're going to say that's 1, 2, 3. And so we're going to have a double bond between carbons number 3 and 4. Now, this is a very important detail. Does this numbering follow our organic rules of numbering? It does not. This is working in the opposite way. This is an instance where I would say, forget about your organic rules for just one split second when you're using this omega numbering scheme. This omega numbering scheme starts from our methyl end. That's carbon number 1, 2, 3. We've got our double bond right here. So now to apply this, we're going to bounce back a previous slide. I'm going to clear out all of my drawings here. When you look at steric, oleic, linoleic, and alpha-linolenic acid, one of them is an omega-3 fatty acid because it has, well, carbon number 18. I'm going to look at that as 1, 2, 3. This is a double bond between carbons 3 and 4. Now, have I changed my numbering? Yes, I have, but only for this practice. So alpha-linolenic acid is an omega-3 fatty acid. Linoleic acid, by contrast, 1, 2, 3, 4, 5, 6. So this is an omega-6 fatty acid. Oleic acid, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is an omega-9 fatty acid. Now, if you're looking at this, I just said 9 and crossed out this carbon. You're absolutely right that that is confusing because, well, isn't this carbon number 9? It is. But where is that 9 starting from? It's starting from this carbon. So 18 carbons, if you count one way and you land at 9 and you count the other way, you're going to end at different carbons. Okay, so omega-3 fatty acids or omega fatty acids are also known as N fatty acids. For example, if you see something like this, N-3, that is a fatty acid, C16:1, 16 carbons long, 1 double bond. Where is that double bond? It is found on our 3rd carbon from the end. Now, what gets a little bit confusing is when you see something like this, C20, okay, so it's 20 carbons, 5 double bonds, okay, that's a lot, N-3. Oh, crap, where's that start? Oh, man, that's tricky. You're not wrong. Okay, where you go with this is this doesn't tell you explicitly where the other double bonds are. Instead, what you need to do with this is say, okay, here's carbon 18 or 20. That's 20, 19, 18, 17, 16. Okay, so if we go with this as number 20, n minus 3. I did not draw 20 carbons there. I'm just starting from one end. I'm going to say 1, 2, 3. So there's one double bond. Okay. Now, with any naturally occurring fatty acid, I have non-conjugated double bonds. So I'm going to go with a double bond. Follow that with 2 single bonds, and then another double bond. So here what I have is 2 of those 5 double bonds that I need to place. Are there more? There absolutely are. Does this tell me explicitly where those double bonds are formed? No, it doesn't. And that's one of the downsides of the omega numbering scheme, because it kind of serves as like a gatekeeper, in the sense that it's like, well, you have to know that naturally occurring fatty acids are not conjugated. If you don't know that and you see this 20:5 n minus 3, you're kind of in trouble. So I just wanted to draw kind of one of the hydrocarbon tails of a fatty acid, which I've done right here. Now, fatty acids, some of the important details about them is that they're hydrocarbon chains. Those hydrocarbon chains are super hydrophobic. They don't like water. These fatty acids or your saturated fatty acids, are going to pack very tightly and form pretty rigid, organized aggregates. So here what we have is a nice cartoon model of a saturated fatty acid and an unsaturated fatty acid. Unsaturated chains are going to bend, and they're going to pack in a less ordered way, and they're going to give a little bit more motion. So on the left-hand side, we have, I always like to think about this as from kind of an energetic standpoint. So I'm going to draw a little box. And that's a nice little box there. Okay. Within that box, I have 5 saturated fatty acids. Okay. So if I think about this as each one of these having a lot of energy, saturated fatty acids are very densely packed kind of energy cells. And that's great. Now, if you have any friends who are like I have a friend who she is a long distance triathlete, and she eats a diet that has lots of eggs, that has lots of steak, and she is just, I need lots of saturated fat because I run for very long distances. I swim and ride for very long distances as well. Makes sense. I also have friends who they play a bit of what's the game? Call of Duty. And they maybe there's like a mentally stimulating part of it. But they don't need as much energy as the person who's going out and running 15 miles. So that person who plays Call of Duty, their diet should be richer in unsaturated fatty acids, specifically polyunsaturated fatty acids. And if you give me for just a minute this box that I drew around these saturated fatty acids, if I were to draw roughly the same sized box over a group or a packing of unsaturated and polyunsaturated fatty acids, let's look at those 2 boxes. I'm going to label them. Well, I'm just going to use these labels, C and D. In box C, I've got 5 fatty acids. Each one of them has a lot of energy associated with them. Box D has 3 fatty acids, less energy. Now, if there's one person who's going to go out and they're going to run 15 miles in a day, they need box C. If there's another person who is going to leave their house 3 times to, go grocery shopping and do other things that they need to do in a given day, but they're not going to run 15 miles, If they consume box C, that's going to be excess energy. That energy is not going to be used. It's going to be stored in their body. Whereas box D, that's more like, hey, I'm going to give you the energy that you need so that you can survive, so that you can function, but I'm not going to give you too much energy. Okay, so polyunsaturated and unsaturated fatty acids are not going to pack as densely as your saturated fatty acids do. Now, with all that to say, here's a nice table with structures, carbon skeletons, common names, and some physical properties of fatty acids. I do not want or need you to know the names or structures of fatty acids. I want you to look at this table with me for just a moment and understand the trends. If we look on the left-hand side of this table, we see carbon skeletons. And I'm just going to circle these first 6. These first 6 are saturated fatty acids. They're 12, 14, 16, 18, 20, and 24 carbons long. Okay? All of them have 0 double bonds. They have really great names: lauric, myristic, palmitic, steric, arachidic, lignoceric acid. Awesome. Fantastic names. These molecules have the best names. Melting points of these fatty acids. Well, 12 carbon long saturated fatty acid at 44.2 degrees Celsius. So let's see, if it's like 98 degrees outside, that's Fahrenheit. We're looking at like 39 degrees Celsius, I think. So if you had dodecanoic acid, or lauric acid as it's commonly known, that would be a solid outside. Now, 14 carbons, and you had N-tetradecanoic acid or myristic acid, that would also be a solid outside, because that has a melting point of 53.9 degrees Celsius. Hexadecanoic, octadecanoic, icosanoic, and tetracosanoic. Yeah, tetracosanoic acid. I feel like I was about to say Cosa Nostra, which I think is organized crime, and it's in like The Godfather and whatnot. If you look at all of these saturated fatty acids, what do you see about their melting points? Their melting points continue kind of creeping up. So as we add more carbons, we see that their melting points continuously increase. 24 carbons long, 86 degrees Celsius. That's a warm one. You're getting lots of like that. That is definitely going to be a solid at room temperature. It's definitely going to be a solid outside. You're talking about, heating that up. Yeah, quite a bit, almost to a boiling point of water. Now, let's look at the bottom portion of this table. We've got 16:1, 18, then 18:2. Okay, so let's look at those 3. 16 carbons, 1 double bond. What is your melting point? It ranges between 1 and 0.5 degrees Celsius. That's not a joke. That's not like 1 or 0.5 minus something else compared to some standard. That is instead like 1 degree Celsius, which would be like 34 degrees Fahrenheit. So just above the freezing point of water. That's where this is going to be. So if you had this palmitoleic acid at room temperature, if you had if I had palmitoleic acid and I put it in my hand, it's going to be a liquid. That is going to be a liquid at room temperature, because room temperature is about 23 degrees Celsius. So that is definitely a liquid. It has melted. Now let's take that palmitoleic acid and add 2 more carbons to it to make oleic acid. 13.4 degrees Celsius. Okay, so the only difference between those two is 2 more carbons. So we have 1 double bond in 16:1 and 18:1, and the temperature difference between their melting points is about 13 degrees. When you add 2 more carbons, you see the temperature or the melting point increase. Okay, now let's go to 18:2. Linoleic acid. That has a melting point of between 1 and 5 degrees Celsius. Between 1 and 5 degrees Celsius, that is going to transition, well, that's going to melt between 1 and 5 degrees Celsius. So when we added that second double bond in, now I'm going to erase all my writing. When we added that second double bond here, what happened to our melting point between these two? It dropped. It almost got to a level similar to that of 16:1. So from the top half of this table, there's one trend that you can take away from it. Increase the number of carbons, melting point goes up. Increase the number of double bonds, melting point goes down. We see that from looking at the top half of this table and the lower half. And then as we dig deeper into the lower half, 18:3, so 18 carbon long fatty acid with 3 double bonds, so the alpha linolenic acid, that has a melting point of negative 11 degrees Celsius. So at negative 11 degrees Celsius, that has a melting point that is lower than water. So that's definitely something to account for. And this is going to be the trend that you need to, like, this is the information I want you to take from this table. I don't want you to say, okay, I know what lignoceric acid is. I know what alpha linolenic acid, alpha linolenic acid. I know what arachidonic acid is. I want you to know what are the trends. The trends are if you increase the number of carbons, your melting point goes up. If you increase the number of double bonds, your melting point goes down. Then between the two, the number of double bonds is going to be kind of more of a priority or higher influence. And that's going to change your melting temperature more. Now, here's just that table, but with a slightly different perspective. It's all the same information. It's all the same common names, and melting points are roughly going to be the exact same. There's a little bit of a difference, but this is the same table. Okay, now we've talked about the omega numbering scheme. We've talked about physical properties of these fatty acids. We've talked about the nomenclature 18:0, 18:1. We're going to add in another numbering scheme that some people like a little bit more. Now, this N-9, that's our omega scheme. Delta 9 is a numbering scheme, another numbering scheme. If you look at these, omega -9 starts here. And this is where carbon number 9 is. That's the carbon number 9 starting from this one right here when you say this is number 1. Okay, now the delta numbering scheme. Some people like the delta numbering scheme a little bit more because when you get to a polyunsaturated fatty acid, the delta numbering scheme provides a little bit more information. The delta numbering scheme explicitly points out where your double bonds start. So delta 9, okay, there's my double bond, and 12, there's my other double bond. Okay, when we get to a polyunsaturated fatty acid, delta 9, 12, and 15. Now, this is where the kind of the bottom falls out of the omega scheme, because the omega scheme, like I said a little while ago, is kind of like a gatekeeper in the sense that it says, okay, well, what you have to have some information. If I say delta, or if I say omega -3, that's all the information I'm going to tell you. Even though this one, 18:3, omega -3, or N-3, 1, 2, 3. It tells you where the first of your 3 double bonds are. It doesn't tell you where your second and third are. Why not? Because what it's telling you is that this fatty acid follows the pattern of double, single, single, double, single, single, double. And that's where your double bonds are going to be found. So I just want to caution you about these two different numbering schemes. N or omega tells you where your first one is, and that's it. The delta numbering scheme tells you explicitly where all your other double bonds are. Now, a very good question, or a very valid question for this right here is, well, why do we have both? The reason is because biochemistry, think about biochemistry as, well, it's a hybrid of chemistry and biology. Okay, hence biochemistry. Now, the second part of this, the second part of biochemistry as a field, is that there are some people who arrive at biochemistry because they really like understanding the chemistry of a biological molecule. There are other people who arrive in the field of biochemistry because they studied nutrition. And so these two different numbering schemes are more commonly used in different fields. The delta numbering scheme is more common for chemists, and the omega scheme is a little bit more common for people who study nutrition. Um, and so that's why there's two of them. Okay, so that's our individual building block for our individual fatty acids. Fatty acids do not polymerize. You do not make a polymer of, 500 fatty acids. But instead, the closest thing that you get to a polymer is a molecule known as a triacylglycerol or a triglyceride. This is a molecule made up of glycerol and fatty acids, 3 fatty acids. So glycerol has this nice backbone where it's got these 3 hydroxyl groups. Those hydroxyl groups are going to be modified to accept a fatty acid, and that's where we make a triacylglycerol. Here is an example of a triacylglycerol on display. This has 1 saturated fatty acid, that's 18 carbons, then 1 with 2 double bonds, and it's 18 carbons, and then another monounsaturated fatty acid with 16 carbons. Fatty acid triesters of glycerol, that's what a triacylglycerol is. These contain 2 or 3 different types of fatty acid residues. Now, melting temperature of fatty acids, between different types of fats. So animal fats, they have a high percentage of fatty acid residues. Plant fats, they have a high percentage of unsaturated fatty acid residues. The melting temperature of fatty acid varies with degree of saturation and chain length. So this is not too far from what we've previously said. So here what we show in this figure is what is the overall composition of olive oil, butter, and beef fat. So we've got 3 different kind of renderings. We've got 16 and 18 saturated, 16 and 18 unsaturated, 14 to 4 saturated fatty acids. Now, if we look at olive oil, it's mostly this one right here, our 16 and 18 carbon long unsaturated fatty acids. Now, in beef fat and butter, you have a higher percentage of this guy right here. Then, last but not least, your saturated fatty acids that are anywhere from 4 to 14 carbons long, they're going to be here. Of all of these different types of fats, or these sources of fats, butter is going to have the highest percentage of shorter fatty acids. It's pretty uncommon for short fatty acids to be present, which I believe, what is it? That's this, let me, just a second. Sorry, I'm having to Google the exact term. Anyway, but what I was going to say, or what I'm now going to say is, if you follow any sort of like nutrition people on Instagram or YouTube or anything like that, there's lots of folks who are like, oh, I put a stick of butter in my coffee, and that's what wakes me up in the morning. An alternative to that, what people use is MCT oil, and that's medium chain triglycerides. Those medium chain triglycerides are within this range right here. So it's a lot of these shorter fatty acids, which is why they use butter. and throw butter into their coffee. Um, medium chain or MCT oil. I think that it's just lots of shorter fatty acids or triglycerides that have shorter fatty acids. Um, I know nothing about the efficacy of that. I just think about the idea of eating butter, not on bread or something else, like biting butter. I just think, no, thank you. I'm not interested in that. Put it on a pancake, on the other hand. Whew. Okay. Biological role of triglycerols, triacylglycerols. I have a tendency to say triglycerols. That's not a word. It's triacylglycerols or triglycerides. I like to, in my mind, just take those two words, throw them in a blender, and take out a word that is not real. Triacylglycerols function as energy reservoirs in animals. The fat content of normal humans allows them to survive starvation for 2 to 3 months. Triacylglycerols function to insulate, and that's what's going to, keep people warm, keep bodies warm. Just anecdotally, there's a guy that his story, I've seen it online a handful of times. Cannot remember his last name is I forgot his name at the moment. Um, anyway, this guy's story is that for under the supervision of some physicians, this guy basically fasted for a full year, for 367 days, I think, and he survived. He lived because he just had so much fat stored that his body was able to, break that down. And he took, he drank water. He had nutritional supplement, like vitamins, necessary vitamins for metabolism and for life and everything like that. But he had so much fat stored on his body that he was able to process that. Barbieri, I think, was his last name. Yeah. Oh, thank you, Christian. Thank you very much. Yes. Um, I promised that I remembered it before you typed it into the chat, but it wasn't a race. Okay, so anyway, thank you, thank you. So that's just kind of an anecdotal story, and then there's also like lots of people online who are like long-term fasters. Anyway, triacylglycerol's function is to insulate. Olestra years ago. This is whenever I was a teenager. Frito-Lay is a company that obviously makes Doritos, and Doritos are wonderful and tasty. And there were chemists working at Frito-Lay who were like, people love our chips. They love them, but they don't like all of the fat content. We need to do something about that. And then one guy was like, or one person said, what we need to do is we need to make a fat substitute that basically people will eat, and it'll give them the sensation of eating something that has fat. It will taste the same, but it won't have the caloric density. It won't be as taxing. So they came up with this substance called Olestra. And Olestra is basically, I'm going to draw a very crude model of it. Structurally, it was 2 sugars, 2 rings. So there's these rings. And if you think back to your structures of rings, every single one of your carbons has a hydroxide group. And I'll just draw like 1 or 2 just for the sake of the model. So we got these hydroxide groups. Now, let's jog back for just 1 slide, 2 slides. Okay. Glycerol, 3 hydroxide groups. Those 3 hydroxide groups can react with a carboxylic acid to make an ester. You basically throw this carboxylic acid in place of this hydroxide group. And so these chemists at Frito-Lay said, we're going to take a molecule like a sugar, and we're going to basically throw a bunch of fats onto these hydroxide groups. And they were like, okay, cool. and they started packaging it into food and specifically into chips. And they made these chips that were called Wow. And they had like Wow with an exclamation mark. They were Wow brand Doritos. And these were pretty big in like 1994 to like 1997 or 6 or something like that. And the Wow brand chips were just a hit because their fat content was super low, because your body gets these weird molecules and says, I don't know what to do with that. So I'm not going to break it down because it's not a fat. I see these fatty acid chains, these there's my fatty acid chain, but nothing else of it doesn't look right to me. And these were super popular. And then stories started creeping in where people were like, I like the Wow brand chips, but they make my stomach very, very angry at me. And so definitely have some like digestive issues after I eat Wow brand chips. And then the stories got louder. People are like, I think I'm not going to eat Wow brand chips because maybe that's the source. And lo and behold, that was the source. And so, as it turns out, when your consumers tell you that your product makes them have really bad digestive problems, marketing teams struggle to really reframe that as a positive. And so Wow brand chips, they had their time, they were really big, and then they weren't. And they still aren't, because bathroom problems are a tough hurdle to jump over for a marketing team. But that's what Olestra is. It was a fat substitute that was based on carbohydrates. Now, if you've ever read, this is kind of like I like to think of this almost as my pop culture slide, because this allows me to bring up a couple of things. If you've ever read the book or seen the movie Fight Club, they talk about this process known as saponification, or it's also known as rendering, where they took triacylglycerols. They took fat from, they actually, in the book and in the movie, they took it from um, liposuctions and would treat it with aqueous sodium hydroxide. And that aqueous sodium hydroxide plus these triacylglycerols would give them a bunch of glycerol and sodium salts of fatty acids. So it would give them these nice sodium salts of all these individual fatty acids. And what they would do is they make soap from it. And if you've ever been to Cincinnati, Ohio, they have the Flying Pig Marathon there, because this soap making process, is one of the things that put that city on the map, because Cincinnati is the home of Procter and Gamble, and Procter and Gamble makes absolutely everything. They're like one of the Fortune 5 companies in the world, and not 500, Fortune 5 or Fortune 50 at least. And they got their start with this process of saponification. They would take pig fat and render it with sodium hydroxide to make soap. Now, this is an industrial process. Alternatively, your body takes triacylglycerols and goes through a process known as enzymatic hydrolysis, uses a class of enzymes known as lipases, and produces glycerol and ionized fatty acids. So it releases those fatty acids. So enzymatic hydrolysis uses lipases to make these fatty acids. Now, lipids and fats are going to fall into a couple of different categories, and you can classify them similarly to how we classify, well, everything, but amino acids. We can classify them as polar or non-polar. Triacylglycerols, glycerophospholipids, and sphingomyelins. A triacylglycerol, it's got this fatty acid chain, these R1, R2, and R3. Those are all going to be very non-polar. This backbone is also going to be fairly non-polar. You got this small group as a part of the molecule that's polar. So overall, a triacylglycerol is an example of a non-polar lipid. Now, glycerophospholipid. If you look at a glycerophospholipid, and we're using this term for the first time, you'll look, or what I want you to see is this right here is that glycerol backbone. You've got this fatty acid, which has been added to our glycerol. We've got another fatty acid added to our glycerol. And then we've got a phosphate group and an X head group. Okay, so what we have here is a molecule that is very similar to a triacylglycerol, but this whole thing right here makes this molecule polar. So this is a polar molecule compared to a non-polar molecule. Now, so glycerophospholipid, let me go ahead and erase all my. What to sneeze? Nope, I'm not. Okay, I'm gonna change the colors. There we go. Change color to green. Okay, so green are our polar ones. So glycerophospholipid is polar. The last molecule is known as a sphingomyelin. A sphingomyelin has some features that make it similar, but then also have some features that make them a little bit different. We got this backbone here, which is similar to our glycerol backbone. We've got the 3 carbons, but these 3 carbons, they've got some other things added to them. One, we've got an amine here, and then a palmitate, which palmitate is a 16 carbon long fatty acid that has been added to a sphingomyelin. Now, palmitate is the one instance where I'm like, I want you to know the common name because it's unique here. A sphingomyelin is always going to have a palmitate on this amino group on this kind of glycerol backbone. It's also going to have this chain right here that is 1, 2, 12, so 14, 15 carbons long. And then, so these 2 groups that those are going to be fairly non-polar. But then this thing over here, this phosphocholine head group, a phosphate group, well, PO4 3-, that's going to be polar. And then the rest of this head group right here, that's also going to be polar. So we've got these head groups that are polar that kind of cause a little bit of a problem in terms of the polarity of this overall molecule. So this molecule, this whole thing, a sphingomyelin, is also going to be polar. So of these 3 different classes of fatty acids, or different classes of lipids, triacylglycerols, non-polar. Glycerophospholipids and sphingomyelins are going to be polar. Your non-polar lipids, like your triacylglycerols, are going to be tremendous energy stores, whereas your polar groups are going to be the basis of bilayers, lipid bilayers. Now, if we talk about a glycerophospholipid, well, the construction of a glycerophospholipid is visualized really well here with glycerol 3-phosphate. That glycerol 3-phosphate has a phosphate on position number 3. Then you're going to add 2 fatty acids to carbons 1 and 2, and you're going to make a glycerophospholipid. That molecule can be modified where this phosphate group is. When we talk about a glycerophospholipid, we're going to focus on that group because that group is where we're going to have modification. Glycerophospholipids are the major lipid component of biological membranes. These are amphiphilic molecules with non-polar aliphatic tails and phosphoryl X heads. So here, if we look at the top of this molecule, we've got that group, we've got this group right here. Where that phosphate and where that X are, that's where kind of all the craziness is going to go. Where this X is, I don't know why my computer is doing these weird symbols. That X can be replaced with any one of these things. And as it can be replaced with any one of those things, the interactions or the types of interactions that these glycerophospholipids can have are going to vary tremendously. So these are going to produce different phospholipids. One phospholipid known as phosphatidic acid, another phosphatidylethanolamine, phosphatidylcholine, phosphatidylserine, phosphatidylainositol, phosphatidylglycerol, and diphosphatidylglycerol. These are all different molecules. Now they serve different purposes. For instance, phosphatidic acid is something that is found in a membrane. And if I remember correctly, it's healthy cells. It is displayed, it's on the inner side of the membrane. Whereas in cells undergoing autophagy or cell senescence, they're going to flip to be on the outer leaflet of a membrane, which this is not details that I need you to know, but just for context. Phosphatidylainositol, I remember looking this up a few years ago. Like phosphatidylainositol is involved in lots of signaling, as is the case with most of these glycerophospholipids. But phosphatidylainositol also has a industrial application, and that is it is a major source for cutting drugs. And whenever you hear cutting drugs, it's like you take your pure substance, then you cut into it, you add something else to make it look like you have more of it. So your 1 pound of cocaine, if you cut it with half a pound of phosphatidylainositol, well, then you're going to, a drug dealer is going to be like, okay, cool, I got 1.5 pounds of cocaine. I'm not going to tell anyone that half a pound of it is phosphatidylainositol, because if I do, then they might be on to me. And yeah, anyway, there we go. Sphingolipids. These are built on a molecule known as sphingosine. So on the left-hand side, you see sphingosine. That sphingosine, where this amide is, that's where you're going to add your palmitic acid. That palmitic acid is going to be added to that N right there. That's going to make a molecule known as a ceramide. So a ceramide has this 3-carbon backbone, and then this 15-carbon long tail, and then this amine with a fatty acid on it. Sphingolipids are major membrane components. They are derivatives of the C18 amino alcohol sphingosine. The basic unit of one of these sphingolipids is a ceramide. And these sphingolipids have a phosphocholine head group. Phosphocholine is an example of a head group. Sphingomyelins, they have a head group of phosphocholine or phosphoethanolamine. So that's where this thing right here that I just circled, that can be modified, or that can be swapped out to make something else. Now, the point of this is that if we jump back a tad, our polar lipids are the parts of bilayers. So when you think about a lipid bilayer, I want you to think, like, to take that word bilayer and dissect it. Well, bilayer means 2 layers. And when you think about a membrane, well, you've got your inner side and your outer side. If something is projected, or if something is like on the inside and then it goes to the outside, that's a way of like signaling to other cells, hey, this is what I'm doing. Whenever I circle something like phosphocholine and I say, oh, well, this can be modified, that is because phosphocholine or phosphoethanolamine, if those head groups, if phosphocholine is the head group that's projected on the outer side of a cell membrane, that is going to communicate one thing to adjacent cells. That phosphoethanolamine communicates a different thing. So we have these 2 different communication mechanisms and 2 different sort of signals that the cell is projecting outward. Like, hey, here's what's going on. Alternatively, if this was present, here's what it would be saying. So sphingolipids are communication methods or communication tools. Now, with them being communication tools, they are key to the cell cycle. They are key to developmental processes. So sphingolipids and glycerophospholipids are signaling molecules. Think about them in that sense. Cerebrosides, they have a head group, a single sugar such as glucose or galactose. Now, here is an example of a cerebroside or a ganglioside. You know what? I'm going to move past this one. So what I want you to know about glycerophospholipids and sphingolipids is that they communicate. Now, we will go through this. Gangliosides. So what I want you to do is, okay, sorry about this. I'm going to clear all my drawings off of here. And now what I'm going to do is I'm going to highlight the molecule that I want you to think about, and then know that the part that I did not put a box around, that's the phosphocholine head group. So that could be a different type of head group. In the case of, or it could be a different molecule there, and that's going to communicate a different thing. When that part that I did not put a box around consists of something else, it's going to communicate different things. Now what I'm going to do is I'm going to put a box around all of this. So I want you to look at this and see that we have a 3-carbon backbone, we have a 15-carbon long chain, and then we have a fatty acid. In this case, it's stearic acid. It's typically stearic or palmitic acid off of that amine group. Okay, if we bounce back, here what we have is our 3-carbon backbone, our 15-carbon tail, then our amine, and in this case, it's palmitic acid, okay? So that sphingomyelin, that is the heart of a molecule known as a ganglioside. Now, gangliosides get very complicated, but if you see that heart of your molecule, you're going to be in good shape. That's a good place to start. Now, this head has a head group of 3 or more sugars, one of which is going to be sialic acid. Here is sialic acid. So this head group, so in place of the phosphocholine head group, the head group is, now I'm going to clear all my drawings and I'm going to circle just the head group in red. There is the head group. A ganglioside has that heart molecule plus this head group that consists of 3 or more sugars. One of those sugars is sialic acid. The molecule that I'm showing you here has a total of 5 sugars. Glucose, galactose, N-acetyl galactosamine, galactose, and sialic acid. Okay. Gangliosides are primarily components of membranes on cell surfaces and constitute 6% of brain lipids. These act as receptors for pituitary glycoprotein hormones that regulate physiological functions. Okay, so now this molecule right here, this ganglioside, we're going to look at this in the next slide, because this molecule is a big part of brain cell membranes and brain development. Here what we have is the process by which a ganglioside is degraded. Now, typically, if we were to take this molecule right here, that looks like a narwhal, and I didn't intend for it to, so something's going on with my mouse. But that molecule that I just circled is this molecule right here, where we have galactose. This is galactose. Sialic acid right here. This is sialic acid. N-acetylgalactosamine. This is N-acetylgalactosamine. Here's my other galactose. Here's my other galactose. Here's my glucose. Here's my glucose. Okay. Now, what is supposed to happen is that this molecule that I have circled, it is supposed to be metabolized by beta-galactosidase, hexosaminidase A, ganglioside neuraminidase, beta-galactosidase, and glucocerebrosidase, and it's supposed to leave behind a ceramide, which is my heart molecule down here. That ceramide is supposed to be left at the end of it all. Now, what happens is some of these different enzymes are inhibited or non-functional. And in the case of beta-galactosidase, if this enzyme is non-functional, it's going to lead to a disease, a developmental disease known as generalized gangliosidosis. The next enzyme in this process takes and removes this N-acetylgalactosamine, so this sugar right here. So if somebody has a functional beta-galactosidase, this galactose is going to be removed. Clear my drawings. This galactose is going to be removed by beta-galactosidase. Okay. Now, in the event that somebody has a functional beta-galactosidase, but a non-functional hexosaminidase A, that means that this is gone, but this will remain. And that's going to lead to the development of the disease known as Tay-Sachs disease. These are all diseases that you may have heard of before as having a strong genetic component. And there are certain populations of people who you're more likely to have this disease if you are from Eastern Europe or something like that, or this particular region of Hungary or something like that. That's because, well, these are either dominant or lots of people are carriers of these diseases. And so my point is that these are the enzymes that are implicated in the breakdown of gangliosides. And if these gangliosides are not broken down properly and you don't end up with a ceramide, then any number of these different diseases can reveal themselves and can be a source of a developmental problem. So defects in sphingolipid degradation leads to accumulation in various tissues causing diseases. All right. Now, the enzymes that are going to break down triacylglycerols and glycerophospholipids are known as lipases. Here what we have is a glycerophospholipid. And we know it's a glycerophospholipid because here's our glycerol, and here's our phosphate, and then here's our chains. We have a total of 4 different enzymes that we need to know about. If you look at this slide, you'll see a molecule going to the formation of a different molecule. Phospholipase A2 is acting on carbon number 2 and releasing this fatty acid from carbon number 2. That really looks like a narwhal now. So that's going to give us a lysophospholipid. So that's where phospholipase A2 is. Phospholipase A2 is specifically acting on carbon number 2 to release a fatty acid from a glycerophospholipid. Phospholipase A1, by comparison, phospholipase A1 is going to act on carbon number 1 and release a fatty acid. Phospholipase D and phospholipase C, these are both acting on carbon number 3, but The difference between them is where they are going to cut. Phospholipase D, if that cuts, that's going to leave behind the phosphate group and release whatever head group is present. Whereas phospholipase C is going to cut on the glycerol side of the phosphate, and so it's going to release a phosphorylated head group. So that terminology right there, phospholipase C releases a phosphorylated head group, whereas phospholipase D releases just the head group. D is just the head group, and C is the phosphorylated head group. I want you to know where these different phospholipases cut and what their possible products are. Now, cells are constantly degrading and resynthesizing membrane phospholipids and sphingolipids. These are broken down so that they can be used to build up. I want you to know where these lipases cut. Now, lipids also have non-membrane functions. We talked about this a little bit. Signaling lipids, they can be lipid cofactors. They can also be pigments and antioxidants. Vitamin A is an essential pigment for vision. Vitamin K acts as an antioxidant. If I remember correctly, your major fat-soluble vitamins are A, D, E, and K. I think that's then so we'll get into those in just a second. But a signaling lipid. Eicosanoids are 20 carbon long fatty acids that act at low concentration and are involved in the production of pain and fever, regulation of blood pressure, blood coagulation, and reproduction. These are produced and used locally. So here what we have is a glycerol phospholipid, right? Glycerophospholipid where we've got a polar head group, and then we've got phospholipase A2 that comes along and cuts off our fatty acid there. That fatty acid is 20 carbons long. It follows the double, single, single, double pattern. It's a polyunsaturated fatty acid, 4 double bonds. So this would be C20 colon 4. This is a fatty acid known as arachidonic acid. This arachidonic acid is going to act in a couple of different directions. One way that it can act in is it can cyclize to form prostaglandin E1 or thromboxane A2. Prostaglandin E1 and thromboxane A2, they are going to help your body produce a fever, and these will be produced and you might feel pain where they are going to be concentrated, but you take a drug known as a non-steroid anti-inflammatory drug that blocks the formation of these two. The enzymes that produce prostaglandin E1 and A2 are known as cyclooxygenases. These are COX enzymes. NSAIDs, or your non-steroid anti-inflammatory drugs, are COX inhibitors. They act to inhibit those enzymes. So that arachidonic acid could instead be circulated through your body and not really do the same thing. Cholesterol is a class of compounds. These are based on core structure consisting of 3 6-membered rings and 1 5-membered ring, all fused together. So there's our example of rings A, B, C are your 6-membered rings, and ring D is your 5-membered ring. Every cholesterol is going to have that same general structure. Then you're going to have some modifications either in your head group or this alkyl side chain. Cholesterol is the most common steroid in animals and precursor for all other steroids in animals. Plants do not produce cholesterols, they produce phytosterols. So they produce sterols, but they are not cholesterol in the same way that we make cholesterol. There are some that people will take nutritionally to control your cholesterol serum levels. And then, yeah, so these can be used by people, but they're different from sterols that we produce. Stigmasterol, beta-cytosterol, and campesterol are your common phytosterols. There are steroid hormones: testosterone, estradiol, cortisol, aldosterone, prednisolone, and prednisone. Steroid hormones bind to specific or highly specific receptor proteins in the nucleus, regulating gene expression and metabolism. Major groups are the sex hormones and those produced by the adrenal cortex. So modifications of these are molecules that are commonly referred to as performance-enhancing drugs as well. Testosterone modifications of that, and you get a drug that gets you banned from the Tour de France. Your lipid-soluble vitamins A, D, E, and K. A serves as the site of primary photochemical reaction in vision. D regulates calcium. E serves as an antioxidant. K has a regulatory function on blood clotting. Vitamin D is actually a group of structurally related compounds that play a role in the regulation of calcium and phosphorus metabolism. The most abundant form in the circulatory system is vitamin D3. D3, that might be the one that you take a supplement of, and that is your cholecalciferol, and that is going to be modified. So your vitamin D, 7-dehydrocholesterol, is going to react with UV light, undergo a pair of steps where this cholesterol ring structure basically opens up, and you get this vitamin D3. Now that vitamin D3 is going to undergo a pair of steps, one in the liver and one in the kidney, and that's going to give you 1,25-dihydroxy vitamin D3. So that is going to be the one that your body's going to benefit from. The best understood role of vitamin A is its participation in the visual cycle of rod cells. The active molecule is one known as retinal, which is a vitamin A aldehyde. Retinal forms an imine with an NH2 group of the protein opsin to form the visual pigment called rhodopsin. Okay. The primary chemical event of vision in rod cells is absorption of light by rhodopsin, followed by isomerization to the 11-cis double bond of the 11-trans double bond. Okay, so when it comes to basically the takeaway for this, or what I want you to know about this, is you, day in and day out, will find carrots and eat those carrots. And those carrots are rich in a compound known as beta carotene. This is beta carotene. Your body is going to process that beta carotene and split it right here into two vitamin A molecules known as retinol. That retinol is going to be oxidized to an aldehyde, so that alcohol is going to be converted into this aldehyde. Other than that, it's also going to be oxidized, and you're going to get a double bond here, or it's going to transition to the cis retinal. Then what's going to happen is, under exposure to visible light, so approximately 400 nanometers to 750 nanometers, you're going to form trans retinal. That trans retinal is going to be a neuronal signal to the brain that's going to be a way of stimulating, or a way of kind of detecting any sort of visible light. The presence of that trans retinal is going to be your signal to, yes, there's visible light here. Now, vitamin E. So we've gone D, A, E. Vitamin E is a group of compounds of similar structure. The most common is alpha tocopherol, vitamin E right here. This is an antioxidant. It traps or a free radical, and radicals formed as a result of the oxidation of O2 of unsaturated hydrocarbon chains in membrane phospholipids. Now, if you look at this long hydrocarbon chain, that's what makes it very effective for capturing these free radicals. Now, by virtue of having these long hydrocarbon chains, that's how it's going to work as an antioxidant. K is also going to work as an antioxidant. And these long hydrocarbon chains, these isoprene units, these 5-carbon long units are common structures that are seen in pigment molecules and in electron carriers in general. If you go on to take a metabolism class, you'll learn about something known as ubiquinone that is involved in the electron transport chain. So after the Krebs cycle, the oxidative phosphorylation, you'll use this coenzyme Q to continue that process. Now, I'm going to stop right there because membranes is going to be where we kick things off next week. So the end of our content for this week and this exam is going to be slide 28. So I've stopped my share. I'm also going to stop my recording right now.